Hi, Wen. This is Station 6, our controller design. My name's Beth.
My name is Brian.
And I'm Jose Aguilar. For this first slide, I'm going to talk about the introduction and the lab goals for Lab 5. The design specification had to meet the following criteria. The controller had to reach 12 radians per second with zero steady state error. It had to obtain an overshoot under 2%, a rise time greater than 0.1 seconds in order to guarantee that it meet their adequate speed and slope requirements. It also had to have a settling time of less than 0.2 seconds, and we need to use less than 24 volts throughout the whole experiment. The control development. Throughout the semester, we were in charge of finding the correct controller to use. In Lab 1, we identified key mechanical parameters of motor systems. In Lab 2 and 3, we analyzed frequency responses and tested proportional controls. Lab 4 was getting introduced to different types of controllers, such as the proportional derivative, proportional integral, and some other controllers. And in this lab, in the last 5, we had to combine all of them.
So our design process takeaways, what we learned from these labs is that proportion control was simple but had steady state error. A PI controller removed error, but it slowed the response down. A PD controller gave fast dynamics, but the system became sensitive to noise. And then a PID offered the best performance, and then we added a low pass filter, which mitigated the noise that was issues in other different controllers.
So we chose the PID controller with the filter as allowed us to get a zero steady state error and a better disturbance rejection. The trade-off was sacrificing a bit of the response speed for a more long-term accuracy and system stability. Simplifications we used was the model was linear and time invariant. There was friction and back EMF, which were treated as a constant. And disturbances can be modeled as a constant voltage offset. For the customer, we also recommend the PID controller with a filter as it prioritizes accuracy and steadiness over time. And the filter stabilizes the noise and tunes it to be steady.
So looking into the future, I just want to summarize what we've learned. Our filtered PID controller met all of our customer criteria and was in strong agreement between theoretical and experimental results, as shown by our plots that we have in our lab. So future application of the process, it can be used in robotic motor control, automated conveyor systems, and small-scale electric vehicles or drones even. This is because the controller strategy that we use is adaptable and can benefit a wide range of applications that demand speed, accuracy, and reliability, all of which are applied to these different future applications. Thank you, Wen. That is it for our group. We appreciate everything you've done for our lab TA this semester.